Welcome back to Differential Calculus. In this video, I want to talk about implicit differentiation. We saw previously that if you are looking at an equation that is not a function clearly on its own, for example, something like, let's use a skinnier pen, 2x squared plus 5y squared is equal to 24. Right? This is the equation of an ellipse. And the most important thing about an ellipse, let's see, square root of 12 is somewhere between 3 and 4. And then we'll have square root of 5, which is somewhere between 2 and 3, giving us an ellipse that looks something like that. Again, the details aren't really that important. That's a very terrible ellipse, but that's okay. The important thing is that I can choose a portion of the ellipse where y is implicitly some function of x. And using that is going to be the tool that allows me to differentiate. On this first example, I'm going to write that out clearly. 2x squared plus 5 times y as a function of x squared is equal to 24. Then I can differentiate both sides of the equation. The derivative with respect to x of 2x squared plus 5 times y of x squared is equal to the derivative with respect to x of 24. On the left-hand side, I can split that derivative up using linearity. So I have 2 times the derivative with respect to x of x squared plus 5 times the derivative with respect to x of y of x squared is equal to, well, the derivative of a constant is just 0. That part's easy. We'll get that out of the way. The derivative of x squared, just following the power rule, is going to be 2x. And then there's another 2 that's been hanging out in front. The derivative of y squared, following the power rule, is going to be 2 times y. But I'm taking the derivative with respect to x, and y is a function of x. So I have to use the chain rule. When I take the derivative of y squared with respect to x, I get 2 times y, and then multiply by the derivative of the inner function, y prime of x. It seems a little bit messy at first, but as you get used to it, it will become second nature, I promise. Now from here, my goal had been to take the derivative of y as a function of x. And I have the derivative of y as a function of x appearing in my equation. So let's do a little bit of creative rearrangement. We've got 4x plus 10 times y of x times y prime of x is equal to 0, which means that 10 times y of x times y prime of x is equal to negative 4 times x. And finally, y prime of x is negative 4x over 10 times y of x, and at this point I'm going to suppress that and just call it y. All right, reducing that fraction, and I get that y prime is 2x over 5y. I almost forgot the negative sign. there we have it. All right, so even when we don't have explicitly a function, we have y implicitly defining a function of x in the general vicinity of the point in question, we're still able to find an expression for y prime. From here, we could likewise find the equation of a tangent line. Right? For a particular value of x and y, things get a little bit messier because we need to explicitly give a value of x and a value of y because there's more than one y value for the x value. But we can use the original equation to verify that that is a point. We can use the derivative to find the slope of the tangent line, and we can write the equation of the tangent line from there. That's what I'm going to do in the next example. But before I move on, I wanted to also point out, I said in this example that I was being very careful writing y as a function of x as I went through. In the next example, I'm going to suppress that. I'm just going to write y. I'm going to remember mentally that y is a function of x, so that when I take the derivative with respect to x, I need to use the chain rule and get y prime. I know that's going to happen. I'm not going to worry about writing it out explicitly because I'm a mathematician. Mathematicians are lazy, and if we can save ourselves a little bit of writing, we're going to. So for example, I'd like you to write the equation of the line tangent to the curve 4xy minus 5y squared is equal to 12 at the point 4, 2. Right. I don't immediately recognize the equation form 4xy minus 5y squared. It's not one of the conic sections I know. It is technically a conic section, it just doesn't quite follow the usual pattern. I do want to start off by verifying that this actually is a point on that tangent line. So I will plug that in. 4 times 4 times 2 minus 5 times 2 squared. 4 times 4 is 16. 16 times 2 is 32. 2 squared is 4. 5 times 4 is 20. 32 minus 20 is 12, which is exactly what we had on the right-hand side. All right, so this is a point on the curve. That's an important first step. Now I can differentiate the derivative with respect to x of 4xy minus 5y squared is equal to the derivative with respect to x of 12. All right, I'm going to talk through this one a lot more than I write through it. If you find it useful to write in some of the intermediate steps, please don't let me stop you. All right, but term by term, the derivative of 4 times x times y. Well, we've got a 4. That's just hanging out there. Then we've got x times y. This is a product of two functions. So we will differentiate using the product rule. The derivative of x is 1 multiplied by y plus x times the derivative of y. The derivative of y is y prime. Then my second term. I've got the minus 5 hanging out. Then I need the derivative of y squared. We saw this in the previous example. The derivative of y squared is 2y, but then because we're assuming that y is a function of x, and we are differentiating with respect to x, we used the chain rule to multiply that by the derivative of y, which is y prime. On the right-hand side, the derivative of a constant is 0. All right, distribute, clean things up a little bit. 4y plus 4xy prime minus 10y y prime is equal to 0. My goal is to solve for y prime, and I've got y prime appearing more than once. So, well, I guess get rid of that 4y first of all. That's going to be in the way. Then factor out the common factor of y prime on the left-hand side, which leaves us with 4x minus 10y. And I can divide both sides of the equation by that. Y prime is equal to negative 4y over 4x minus 10y. For our purposes, that's actually good enough. I can stop there. But I did want to at least mention that if this problem was just asking you to differentiate, that you would probably find an answer in the back of the book that looks a little bit different. There's a common factor of 2 between the numerator and denominator that we could cancel out. And then we could multiply numerator and denominator by -1, getting rid of the negative in the numerator and switching the order of the subtraction in the denominator. Letting us write that y prime is 2y over 5y minus 2x. Is that any better? I don't know. Technically, I guess. But because we're not specifically asked for the derivative, we're asked to write the equation of a tangent line, I would probably have stopped there and just gone right to let's plug things in. Right? Scrolling back up, remember we're looking for the equation of the tangent line at the point 4, 2. So plug in x equals 4 and y equals 2. So we've got -8, we've got 16 minus 20, which is -8 over -4, which comes out as +2. All right, so we've got our slope, we've got the point we need to go through. All that's left is to literally write the equation of the tangent line. Y minus the y coordinate is equal to slope times the quantity x minus x coordinate. And technically that's, again, done, but I'd probably clean up a little bit and solve for y to get that y is equal to 2x minus 6. Right? There is our equation of the tangent line. That's what we were asked for here. We've now got it. This problem was a bit of a mess. This is probably a lot for any one problem, but that's kind of why I think it makes a good example for the video. A little bit of a simpler one for you to try on your own. I would like you to differentiate implicitly the equation 4xy squared is equal to 5x cubed plus 7. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.